Chapter 13 is our last chapter together this semester. Chapter 13 introduces a new distribution, F distribution. The F distribution allows us to perform the ANOVA test. ANOVA stands for Analysis of Variance. The ANOVA test allows us to compare multiple groups together and see if there's a significant difference among the group means. This test uses variances to determine if the means are equal or not. There are 5 assumptions that must be met to use this test. First, each population from which a sample is taken is assumed to be normal. Second, all samples are randomly selected and independent. Third, populations are assumed to have equal standard deviations or variances. Fourth, the factor is the categorical variable, and fifth, the response is the numerical variable. So let's talk about the F distribution and the F ratio. The F statistic is a ratio or a fraction. There are 2 sets of degrees of freedom, one for the numerator and one for the denominator. To perform calculations, we need 2 estimates of the variance: variance between samples and variance within samples. We need a sum of squares, SS, for between and within, and we need a mean of squares, MS, for between and within. The F ratio is equal to the mean of squares between divided by the mean of squares within. Now, we have a lot more formulas that we do need to cover. First, some notation. K equals the number of different groups. N sub j is equal to the size of the jth group. S sub j is equal to the sum of the values in the jth group. And N is the total number of values. X is just one specific data value. Now, to get on with our formulas now that we have some notation, degrees of freedom between is equal to k minus 1, so the number of different groups minus 1. Degrees of freedom within is n minus k, so the total number of data values minus the number of different groups. And then we have sum of squares total. Sum of squares total is equal to the sum of our data values squared minus the sum of the data values squared divided by n. Sum of squares between is equal to the sum of the values in each group squared divided by the number of values in that group. And then we're going to subtract off the sum of the data values in the jth group, squaring that result, and then dividing that by n. Sum of squares within is rather difficult to calculate. The best way to calculate it, though, is the sum of squares total minus the sum of squares between. The mean of squares, the best way for you to calculate it will be the mean of squares between equals sum of squares between divided by degrees of freedom between, and mean of squares within equals the sum of squares within divided by degrees of freedom within. So there's a lot there, but we want some useful relationships for understanding how everything relates to each other. So some useful relationships for if you have a partially filled in table. Sum of squares between is equal to mean of squares between times degrees of freedom between. Sum of squares within is equal to the mean of squares within times degrees of freedom within. Degrees of freedom is k minus 1 for between, and degrees of freedom for within is n minus k. Mean of squares is sum of squares divided by degrees of freedom. So for both between and within, we are using that. And then our F ratio is mean of squares between divided by mean of squares within. The p-value is always going to be found on the calculator. Now, the degrees of freedom can also be calculated by rearranging some of these formulas that we have. So we have sum of squares equals mean of squares times degrees of freedom. So that means degrees of freedom equals sum of squares divided by mean of squares. So if we have this partially filled in table, we could calculate the missing values. So we're missing the sum of squares within, but we could calculate that by subtracting sum of squares total minus sum of squares between. And we could do the same for the degrees of freedom within that we are missing. Then we could find mean of squares by taking sum of squares divided by degrees of freedom for both between and within. And then we can find the F ratio by taking mean of squares between divided by mean of squares within. Now, from just looking at this table, we should be able to state how many groups were being compared and how many total participants there were. There were 6 total different groups that were being compared. We find this from our degrees of freedom between plus 1. Now the total number of participants is our degrees of freedom total plus 1. So there's 79 total participants that were used in this table. Looking at another example, first we would want to find the sum of squares between. We would do this by subtracting. Next, we can now find the degrees of freedom between. We find degrees of freedom between by doing sum of squares between divided by mean of squares between. We get 3. Now we can find the degrees of freedom within, which is 17, and that leads us to the mean of squares within. We find the mean of squares within by doing sum of squares within divided by degrees of freedom within. Now we're able to find the F ratio by mean of squares between divided by mean of squares within. Again, we could ask ourselves, how many different groups were we comparing and how many total participants were there? There were 4 groups here with a total of 21 participants. Let's fill in the missing values for this ANOVA table and round our answers to 2 decimal places. So we can find the missing sum of squares between right away. And then we can find the degrees of freedom between. At this point, we're now able to find the degrees of freedom within. And now we can find mean of squares within. Finally, we're in a position to find F. Let's do another example together where we're practicing finding these missing values. The first missing value that we identify that we can find would be the degrees of freedom within. We find this as 44. We could then jump to finding our degrees of freedom between, but just thinking about the original information we were given, we could also find the mean of squares between. We find the mean of squares between by taking the mean of squares within times our F ratio. Keep in mind we can always rearrange any formula that we have by using algebra to solve for a missing value. Now our degrees of freedom between, we said earlier that we could find, that's going to be 6. Now we can find our sum of squares between. Our sum of squares between, and now we've filled in our table. Now let's look at the 5 steps that we need to do to complete the hypothesis testing that we will do in this chapter. These are the same 5 steps that we've looked at over and over again, except for step 3 looks a little bit different. So we're starting with stating the hypotheses, identifying the claim. Then we state our level of significance, or alpha, and then we're going to state the critical value if we're using the traditional method. And then step 3, we're going to complete an ANOVA table and list the p-value if the p-value method is what we're using. The ANOVA table is what we were just filling in those missing values to. Next, we make the decision the same way we always have, and then we write our sentence. Now, with the ANOVA test, our null hypothesis is always that the means are the same, and the alternative is that at least a pair of means is different. So we'd say the null hypothesis is mu1 equals mu2 equals mu3 equals all the way up to mu k, where k is the number of groups that we have. And the alternative is at least two of the group means are not equal, or we could say at least one of them is different. This just tells us that there is a difference. It doesn't tell us which one is different from the rest or if they're all just not equal to each other. So now let's talk about the calculator. The calculator function in ANOVA can be found by going to stat and then over to tests. This may come in handy later, but first we need to enter values into lists. We want to list the data values in our list, one list for each group. Now this is if you're using a TI calculator. I know some of you might have a Casio calculator. Casio calculators are handled differently. Make sure that you do reference your user's manual or email me if you have questions. Then we can use the ANOVA test. The calculator will now give you everything for the ANOVA table. So let's do an example. A sunscreen company is attempting to improve their formula so that it lasts longer in water. They have 4 lead scientists who each came up with a different formula. In order to see if there's a difference in the time the sunscreen lasts, the CEO collects a random sample of each of the 4 sunscreens. The data is listed below. Test the claim that at least one sunscreen has a different lifespan in water at a 0.05 level of significance. So first we're going to list A in list 1, B in list 2, C in list 3, and D in list 4. Then we'll write our hypotheses. Our claim is that at least one of them is different. So our claim is the alternative hypothesis. We state our level of significance, and then we fill in a complete ANOVA table. Now your calculator uses a few different words. It uses factor, where we use between. And then it uses error, where we use within. Now we are able to make the decision. Our decision is do not reject the null hypothesis. There is not enough evidence to support the claim that at least one of the group means are not equal. Again, we're looking at a sunscreen company that's attempting to improve their formula, and their 4 lead scientists have listed their data below from their study. So listing our hypotheses, our claim is the alternative hypothesis. We list our level of significance, and then we fill in our ANOVA table. Keeping in mind that the calculator uses the word factor, where we use the word between, and the calculator uses the word error, where we use the word within. We're able to make the decision, do not reject the null hypothesis. There is not enough evidence to support the claim that at least one of the group means is different.